So students, good morning. How are you? I hope you are fit and fine and doing your studies at your home. So, in continuation with the video lecture, that is work, energy and power, part 10. In the previous video, we had discussed about the potential energy. What is potential energy? What is gravitational potential energy? How potential energy varies with distance, why the force is taken negative of change of potential energy with the distance, variation of potential energy with the variation of height. We had discussed nature of gravitational force. What is the nature of gravitational force? We had discussed all these things. We had discussed in the previous video regarding the potential energy. In the continuation with same potential energy, we are taking another example, that is energy stored in the compression or stretching of spring. All of you are known to the spring. Spring is known to all of you. What is the spring? The spring is helical shape, just like a helical shape, or in this way also there is the spring, round shape. So these are the springs, and there is a property of this spring that when you load this spring, then due to the weight or due to the force applied on the spring stretches itself from its equilibrium position. When the spring is not under the action of any force, then the spring is called as the equilibrium position of the spring. Now, if the force is applied on this spring, due to the action of that force, the spring stretches itself, and as the spring stretches itself, the mass of the spring is considered as mass of spring considered as zero. Since the mass of the spring is considered as zero, so whatever the energy is stored in the spring while compressing it or extending it is stored in the spring as its potential energy. It is a stored energy stored as the potential energy of the spring. In stretching or compressing the spring, whatever the energy is stored is the potential energy of the spring, and this is the mass of the spring. Mass of the spring is taken as negligible. There is a general, in physics, there is a general concept that each and every thing in this universe tries to remain itself in its lowest energy state. Suppose a person, I am taking an example of a person also wants a human being. The nature of the human being is that he always tries to remain at its rest position, that is in its lower energy state. Clear? So similarly, the spring also tries to remain itself in the lowest energy state. So the lowest energy state is that where energy is zero, and if the energy is zero, means the spring always try to remain itself in its equilibrium position. So when you stretch the spring, suppose you had loaded the spring with mass mg, and if you had loaded the spring with mass mg, there is an expansion in the spring. There is an expansion. This is the expansion, that is x. There is an expansion in the string, and what you had done the work that work done is being stored in the spring as its potential energy, but a force, that is the spring force, which is called as restoring force. Fs is what? Fs is the restoring force, that is the spring force or restoring force, and this restoring force always tries to pull the block of mass m into its original position, to maintain the equilibrium of the spring. Similarly, in the case of compression also, if the spring is compressed, then it also tries to maintain its equilibrium position, and a force Fs acts on the spring to bring the spring into its equilibrium position, that is x is equal to 0. X is equal to 0. So, due to that, a force is being restoring force, and this restoring force does work on the spring. This restoring force does work on the spring to maintain its equilibrium position. So, that work by the restoring force we will calculate, we will find that work done, and after that we will calculate the potential energy stored in the spring. So, let us start our discussion, that is potential energy of the spring. 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 We have to calculate, we have to discuss about the potential energy of the spring. For that, what we had taken? We had taken a massless spring. And one end of the spring is tied with a rigid wall. This is a rigid wall. The one end of the spring is tied with the rigid wall, and the other end of the spring is tied with mass m. And this is the equilibrium position of the spring. Now, another case is that this is the equilibrium position, that is x is equal to 0. Now, another thing is that we had stretched the spring to a distance of x. We had stretched the spring with a distance of x. Stretched the spring with a distance of x, and this distance is x. So, due to the stretching of spring from its equilibrium position to a distance x, a opposite, that is the restoring force Fs is being acted upon the spring. And the third case is, we had compressed the spring of mass m. We had compressed the spring of mass m with a distance x. We had compressed the spring with a distance x, and another restoring force Fs acts on the spring, which tries to maintain the spring in its equilibrium position. So, depending on these three cases, we try to calculate the work done. By the spring force. To maintain the block into its equilibrium position, and that work done is considered as the energy stored in the spring. So, first of all, we will try to understand about the force Fs. So, according to, in the chapter, that is mechanical equilibrium of particles, that is in elasticity, that is the potential energy is elastic potential energy. Whatever the potential energy is stored due to the work done by the force Fs, that potential energy is the elastic potential energy stored in the spring. So in the chapter elasticity we will study quite in detail about this process. There in that chapter there is a rule that is called as Hooke's law. So according to Hooke's law, the spring force is directly proportional to the compression or elongation of the spring. So according to Hooke's law, Hooke's law says what? Hooke's law says that a spring force Fs is directly proportional to x. Fs is directly proportional to x, or you can say that Fs is, since Fs is acting opposite, Fs is acting opposite to the compression or elongation. Look at here, elongation in this direction, so Fs is acting in this direction. Here compression is in this direction, so Fs is acting in this direction. So the spring force Fs is acting in opposite direction of compression and or elongation. So Fs can be written as minus of Kx. Negative sign indicates that spring force is acting opposite to the compression or elongation. Yes, students. Now we had discussed about the compression, and this negative sign indicates that spring force is acting opposite to the compression or elongation, so negative sign is here. Now let us suppose this spring force Fs acting on the body of mass m to bring this mass m into its equilibrium position. A small displacement dx takes place due to the restoring force, or this restoring force, a small displacement dx is acting, or dx by mass m. So the small work done dw can be written as Fs into dx, that is force into displacement, since the displacement is in the same direction. Now what we will do, we have to calculate the total work done. In the movement of this mass m from its initial position to final position. Suppose this is initial position, this is final position, or any final position you can suppose where we want to move the block. So if xi is equal to initial position of the block and xf is the final position of the block. Xf is the initial position and xi is the initial position and xf is the final position of the block. Then we want to calculate the complete work done. In moving the spring from its initial position to its final position, from its initial position to final position. So total work done by the spring force, it can be calculated as total work done by the spring force, it can be calculated as integrating the force Fs into dx from the initial position to the final position, from the initial position to the final position, and it is equal to Fx into dx, it is equal to Fx into dx. So now let us see what will happen, that is x initial to x final, and it can be written as what? Fx can be replaced by minus of kx dx, minus of kx dx. And as you know that students, I had again and again you had told you that x to the power n dx can be written as x n plus 1 upon n plus 1, x n plus 1 upon n plus 1 plus c, that is a constant. In indefinite integral, while integration we will include the value of plus c, but in definite integral this constant been cancelled out because we subtract by putting the upper limit minus lower limit, and by putting upper limit minus lower limit the constant will be cancelled out, and there is no scope of constant for definite integral. So here it is the case of definite integral. So we will do what? Minus constant k is taken out, and while taking the integration of x from x initial to final, it will give x square upon 2, that is x initial to x final. Now look at here students, look at here students. Now it will be what? It will be total work done by the spring, and it is given by minus of k, putting the values of upper limit minus lower limit, then it will be equal to what? X final square divided by 2 minus x initial square divided by 2, and it will become what? It will become Ws, that is equal to k x initial square half k x initial square minus half k x final square, half k x initial square minus half k x final square, and you can say that work done Ws u initial minus u final, u initial minus u final, that is the initial potential energy minus final potential energy. Now means the potential energy is kxi square. Now two different cases we will take here, Suppose I am taking that, the first thing is that if we consider the initial position as the equilibrium position, initial position as if xi is equal to 0, and if xi is equal to 0, then Ws is equal to ui is equal to 0, then Ws is equal to minus half k xf square, and it is equal to minus u final, that is equal to Ws. That work done by the spring force can be stored as potential energy. Clear? It is stored as potential energy. So this is first case, and the second case is that if x final and x initial, x final the final position and the initial position. Suppose the spring we had stressed from this point, it goes to this point, extreme position, and from extreme position because when the spring is here then no force is acting, but as we had stressed it, then it is the initial position. Now by the spring force Fs, the block is coming to its mean position, then again this side the spring position, then mean position, then extreme position. So if one cycle is completed, the spring, that is the spring goes to this side, then equilibrium position, then extreme position in the left side, then again mean position, then extreme position in the right side. Then we are going to complete one cycle, and if one cycle is completed, then its initial position is equal to final position. Means if spring comes to its original position again, then at that case x initial is equal to x final. X initial is equal to x final. Then in that case the work done by the spring is equal to half k x I square minus half k x I square, and both x I square is going to cancel out, and the work done is equal to 0. So the total work done by the spring force is equal to 0 when we are bringing the spring to its same position, same initial position. Now what are the conclusions? First of all, we will draw the graph. We will draw the graph of the force with the variation of distance and energy with the variation of distance. Look at the graph here. First, graph between force Fs and distance moved, distance x. Force between Fs and x. So suppose this is force Fs, and on this axis we had drawn the distance. Since we had studied that Fs is minus of kx, so the nature of graph will be like this. This is the nature of the graph between Fs and x. And if we want to draw the graph between u and distance x. So what you are saying, you are observing that the relation between u and x is parabolic in negative direction. So the nature of the graph will be like this parabolic shape. It is like this parabolic shape. Since ux is proportional to negative of x square. So these are the nature of graph for the variation of force with distance and variation of energy with the distance. Now certain conclusions we are going to draw. We draw certain conclusions from these discussions. So the first conclusion is that a spring force Fs is position dependent. conclusions from this discussion. What conclusions we had drawn? Conclusions. The first conclusion is that the spring force is position dependent. Spring force is position dependent, that is Fs is proportional to minus of x. Fs is proportional to minus of x. Second is work done by the spring force. Work done by the spring force. Work done by the spring force depends on initial and final position. Work done by a spring force depends upon initial and final position, not upon the path followed by the spring while moving from its initial position to final position. And the third one is that for a complete cycle, the work done is equal to 0. For the complete cycle, the work done is equal to 0. Work done is equal to 0 for the complete cycle. So these are all the properties of conservative force. So we can say that a spring force is a conservative force. Spring force is a conservative force. Looking on these properties, the spring force is a conservative force. In spite of the fact that force depends on position, the work done by this force depends only on initial position and final position. One thing you have to take mind, while doing all these things, we always suppose that the surface is smooth. The surface is smooth or frictionless. Because if there is the friction, then certain energy is being lost to overcome the friction also. So then that force becomes not the conservative. So we always suppose the surface is smooth. So dear students, this is all about the work done or potential energy stored in the spring while compression or stretching the spring. Now we will discuss numericals based on this. Yes students, now look at the numerical. Now we are going to discuss about the numerical based on the topics which we had studied. A very simple numerical based on gravitational potential energy. Look at here. A ball falls from height of 20 meter. Find the velocity with which the ball hits the ground. Find the velocity. So simple thing, very simple question. Height is 20 meter and you have to find the velocity. H is equal to 20 meter and you have to find the velocity is equal to what? You have to calculate the velocity is equal to what? So when it hits the ground, then kinetic energy is equal to potential energy. we had taken the example of this, and in that it is released from the rest, and we had calculated the potential and the kinetic energy, the velocity at the bottom we had got under root 2gh. 2gh, this is the velocity at the bottom, and from that we had calculated the kinetic energy, that is equal to half mv, kinetic energy that is equal to half mv square, and from here half m root 2gh square, and from here half m 2gh cancel out and it will become mgh. So kinetic energy is equal to potential energy, and from here we can calculate kinetic energy, half mv square is equal to mgh, m to m cancel out, and v is equal to under root 2 gh. It is equal to under root 2 into 10 into 20 meter per second, and it will be equal to 400 meter per second, and it is equal to 20 meter. So its velocity when hits the ground is 20 meter per second. Now dear students, we will going to discuss the next question. Yes students, now look here, a very good numerical. It is given that as shown in figure, this is the figure, it is in front of you. A canister, this is a canister of mass m, and its mass is given 0.4 kg. Slides across a horizontal frictionless counter. This is a horizontal surface that is frictionless and over which this mass m is sliding with velocity v is equal to 0.5 meter per second. This canister is sliding over this with 0.5 meter per second. It then runs into and compress a spring of spring constant 750 Newton per meter. Its spring constant is given as it is going. Since the work done by the spring as it is compressed to this position, this is the initial contact, and after traveling it is compressed by a distance x, and at this position the canister is going to be stopped. So as the canister is going to be stopped at this position, it means to say that there is a force Fs, spring force Fs acting on that canister to maintain its, as the canister comes in contact with this spring, Fs starts acting, which does negative work done. Fs does negative work done. Fs does negative work done. Why it is negative work done, students? Because force is acting in this direction and displacement is in this direction. So obviously if force and displacement has opposite direction, it means to say that the work done is negative, and as the work done is negative, momentarily this block is going to be at rest after traveling a distance of x. So Fs does negative work done, and canister stops momentarily. Canister stops after covering a distance of x. After covering a distance of x, so this thing is written. What is d? With what distance d the spring is compressed? You have to calculate this distance x up to which the spring is compressed. This distance you have to calculate. So note here that three things you have to keep in mind. The first thing is work done by since it is initial contact, so suppose it is the reference point, so you can calculate, you can take it as 0, xi is equal to 0. So the work done by the spring force, that is equal to minus kx square. This is the work done by the spring force, as from the formula we had calculated. Now the second thing we can find out in this numerical, we can think in this numerical, by work energy theorem there is an work done. That work done by work energy theorem, k half mvi square v minus half mv initial, have final kinetic energy minus initial kinetic energy, that is k final minus k initial. And as the final velocity, as the block is going to be stopped at this point, so third thing is that the final velocity as the canister stops after traveling a distance of x, so final velocity is equal to 0. So the work done is equal to negative of its initial kinetic energy. Work done is equal to negative of initial kinetic energy. So keeping these three facts in mind, we can calculate the value of the distance x. So very simple. Now all these things we had calculated. Then this work done is equal to this work done, and from this work done we can half minus of half mvi square is equal to minus of half kx square, and from here you can calculate the value of x, that is the compression. Look at here. These questions look little bit typical, but after thinking over the facts you had studied, you can easily solve these questions, and in this way you can enhance the concept. So look at here, we can say that consider the canister, so you can say that k by work energy theorem, k final minus k initial, and it is equal to negative of half kx square. Final velocity k final is equal to 0, that is equal to negative of half mvi square, and this is equal to negative of half kx square. Half to half cancel out, this will cancel out, and it will be equal to twice mvi square upon k. Twice is equal to x square, and from here you can calculate under root x is equal to under root twice of m upon k, that is a spring constant, and it is equal to v into vi square, it will be outside. All things you are knowing. So 2 into mass is given as 0.4 kg, 0.4 kg upon 750 Newton per meter, 750 Newton per meter, 750 Newton per meter. Look at here, one thing we are missing here, half to half cancel out, and if half to half cancel out, then there is no any scope of 2. Sorry students, this mistake I had done. So x is equal to then x is equal to vi into under root m upon k. So it is, and k is 750 Newton per meter. into velocity. Velocity, it is given that 0.5 meter per second, 0.5 meter per second, and on calculating it, you will get the value of x. It is equal to 0.50 into 0.02, 0.50 into 0.02 meter, 0.02 meter, and it is equal to 0.0115 cent, 0.0115 meter. So x is equal to 0 point, and if you have to convert into centimeter, then 1.15 centimeter, 1.15 centimeter. Clear, students? So in this way we had calculated, by the help of work energy theorem, we had calculated the distance or compression in the spring when the canister going to strike the spring. So that's all for today's video, students. Have a nice day. Take care.